This is not ideal for you, but hopefully I can talk you through these notes and give you enough to try your worksheet that's on the back of these notes. So first of all, I definitely would love you to read through that paragraph there, but some new notation. So f prime, like we've been talking about here, would just be the derivative of x, right? Well, we're going to see, and we talked about this in our notes, didn't really talk about it much, but dy over dx just means the derivative of y with respect to x. So basically, if we have an equation like y, so that's what that's saying up here, such as y, we could definitely say y prime, but you'll see it a lot of times dy over dx. Or like this right here, basically means take the derivative of y with respect to x, which is the same as this right here. So you might be able to be given like y equals x squared and be told to find this. It's just a fancy way of saying find the derivative. It does come out to 2x, which we'll talk about in just a second. I don't want that to confuse you. But another way to say it would not be given to you as y equals x squared, but basically just say to you, evaluate the derivative, and then they give you the equation or the function right there, and then you get your answer. All right, so just kind of notation at the beginning. All right, and then the differentiation techniques. The big one we're going to get into is this one right here, but before we get to that, just some very basic concepts. The derivative of any constant, the derivative is going to be, you can see right here, all of this is evaluating out to 0. Now, why is that true? Well, think about a horizontal line, because that's what a constant function would be. What is the slope of the tangent line anywhere on that line? It's going to be 0. If you crank out the limit definition of a derivative, it would look like this, if you really want to investigate that, because the two ordered pairs we would pick on top for the y values would just make 0, and then we would get the limit as h approaches 0 of 0 equals 0, and you can process it that way, but you can also think about it graphically. The derivative of a linear function, hopefully you can think about, hey, if I got this line right here, what would the slope of a tangent line be? That's what you're thinking it through, and it's a good thought because it does just come out to m. So basically, if you were to show the limit definition of a derivative, the setup would be like this. The other one, I don't know if I said limit definition of a derivative, but that would be, that was at a specific spot, so that was the alternate form. But either way, these are just basic principles that hopefully you can get down. That would, if you crank the distribution out and evaluate that limit, you'll get just the slope of the original linear function. So those are two pretty basic ones that we'll see come up, but then here's a big one here. It's called the power down method. Now, it's a good thing I am not here to teach you this because you're going to get pretty upset. There is a super fast way to do these problems. Remember when you were given this one on your test, and those of you who have to still take the test, yes, you will still have to show the limit definition of a derivative and alternate forms for these, but it's the concept is power down, and we can actually find this using this very simple method. Watch this. It's called power down because you take the power and you just bring it out front. So see how that became a 3 here, and then you subtract 1 from the power. Boom, 3x squared is the derivative. If you really don't believe me, you can go through the limit definition of a derivative. I will not be doing that right now, but x cubed does come out to 3x squared. You're welcome. So remember, we'd have to put in x plus h on this one, and we'd have to crank it all out, but guess what? We have ourselves just a power down method. So 4 comes out, 4 goes down by 1 and becomes a 3. 4x cubed is the derivative. Super duper fast. Notice how the notation changes. This is the function, this is the derivative. You mean for this one? Well, yeah, we'd have to do x plus h, right, to the 100th in limit definition of derivative with Pascal's triangle, right? No, we're definitely not doing that. What we're going to do is power down. So this comes out front. You get the 100 there, x to the 99th power, and that's what it will come out to do. All right, so basically, you're welcome for that. Or I'm sorry that we have to, but every calculus student goes through the limit definition of a derivative before they get to the shortcuts. But here we are. Root x, remember that's the exact same thing as x to the 1/2 power. So in order to find the derivative of root x, we can do this power down method. So basically it just gets a little trickier. The 1/2 comes out front, but then what is 1/2 minus 1? We get the negative 1/2 power. So then remember, we want to take negative exponents and we want to go to the bottom and become a positive exponent. So here we have 1 over 2x to the 1/2 power, or if we wanted to convert that all the way, we could say 1 over 2 root x. Okay, you can leave it to the 1/2 power for this assignment too. Here's the other thing, this one here, what is 1 over x really? It's really x to the negative first power. Well then, let me get a different color here. Then where does the negative 1 go? When we power it down, it comes out front. So that's a negative 1, x to the negative second power. And then this all comes downstairs and becomes x to the positive second power. So that would be the derivative of the reciprocal function. All right, then over here, notice just the different notation. It says find the derivative of this. That's kind of hard to see on this screen, but that's the cube root of x. So remember, that's going to be x to the 1/3 power on the bottom. So when I bring it up top, it'll be x to the negative 1/3 power. So then we take the negative 1/3 out front right here. Since we have evaluated and powered down already, we don't write the derivative out front of it anymore. It's just equivalent to this here. So that's how we can show that. And then negative 1/3 minus 3/3 or minus 1 is negative 4/3. And then that would have to go to the bottom. As you can see, we're not making you go into the changing that fractional exponent there. That's fine to stop right there. And then this one, this could be rewritten easily as x cubed to the 1/4 power. Remember that? Okay, then it's x to the 3/4 power. So what does the 3/4 do? It comes out front, so we got that there. And then we subtract 1 from the exponent again, and then again bring it downstairs. Okay, properties of derivatives here, pretty straightforward. The notation could definitely mess you up a little bit. But basically what is it saying there is if you have a constant times a function, that's the same as taking the constant out front and then just finding the derivative of the function. So basically, if we look right here, we already did that one. I thought we did. Sorry, no we didn't. Yeah, we did. Sorry, right here. Yep, we did. Told you we did. Okay, so 4x cubed. So this would be 4x cubed times 5, which just makes it 20x cubed. So basically, just take the 5 out in your mind and then take the derivative is the idea. I know you're going to be bringing the 4 to the 5 and multiplying it by 20. Yes, that's essentially what's happening because the derivative is going to end up being multiplied, whatever was in front there. All right, and then addition and subtraction here. Basically, what do you do with addition and subtraction is you can find, you know, if you have two polynomial functions like that, added or subtracted together, or just functions, I should say, then you can take the derivative of one and then add or subtract the derivative of the other. So instead of putting these together, you can literally take the derivative separately and keep the addition sign in between them. Okay, it does not work with multiplication and division. We have some special rules for that, so stay tuned and we'll teach you those soon. But for now, you should have enough to try the back side of this practice. Appreciate it. And again, sorry for being gone today, but hopefully this helped.